Consider the following formula, not P implies P. And so this formula says that two negations make an assertion, essentially. If you say, it is not the case that I'm not walking in the park, not P. It is not the case that I'm not walking in the park, not P. If that's the case, then I'm walking in the park. If I have two negations, I can cancel them out and I get an assertion. So not P gives me P. So this is what this means in general. So presumably we should be able to derive such a formula in our system. How can we do that? Now you can see that this is a implication, and whenever you want to derive an implication, you should always assume the antecedent, assume what's on the left-hand side of the arrow, and try to derive the consequent. So I'm writing here at the bottom, not P implies P. That's what we want to derive. I'm going to assume somewhere up here, not P. This is assumption, let's call it assumption number 1. And then I write immediately above this line, P. So we need to get from not P to P. We need to fill in this gap. Now we know by our notational convention, so the notational convention NC tells us that the formula that has the shape of not A is the same as A implies the contradiction. So not P, which I should probably write as not parenthesis not P close parenthesis, just to be precise, has the shape of a negation. It's a double negation, but you have first a negation here and then a negation again. So by our notational convention, I can transform this formula into a formula of the form A implies the implication. So I can say not P implies the contradiction. A implies the contradiction, not P implies the contradiction. So you see that I removed one negation, and I turned that one negation into implies the contradiction. Now the question is, how am I going to get to P if I have not P implies the contradiction? There doesn't seem to be anything that I can do really, because I have P, I have here, down here, I have not P implies the contradiction. However, here is something I can do. Suppose I assume not P. And why I assume not P will be clear in a second. And I call this assumption number 2. Okay, I have not P implies the contradiction. I have not P. I just assumed is not P, apparently with no reason, but it'll become clear in a second. Just try things out. And I can put these two things together with implication elimination and get the contradiction. All right, I got the contradiction. So now what? The interesting thing is that there is a rule in our system of derivation called Reductio ad Absurdum, called RAA, Reductio ad Absurdum, which means to arrive at a contradiction, So what we've done here, and this is precisely what we've done here, we have arrived at the contradiction. So I created a situation by assuming not P such that it got me a contradiction. The rule of reductio ad absurdum is this. It functions in the following way. If you assume a formula of the shape not A, you go through your derivation and you get a contradiction, then you can say A. So that's the reductio ad absurdum. But that's not all. Once you do that, you can cancel not A. Suppose you've called not A with a certain number I, and so you can index this here, so kind of showing that this is connected to this. So if you assume not A, you get to the contradiction, then you can write below the line A, and you remove not A as your assumption. This is the rule of reductio ad absurdum. Now this rule, I can apply this rule here. So I started with not P, that was my assumption. I got to a contradiction to some other steps. And so by applying reductio ad absurdum to my assumption number 2, I cancel that assumption. And therefore I get P. So this rule allows me, whenever I assume not P or something that has a negation, and I get to a contradiction after that assumption, to remove the negation from my assumption and then cancelling my assumption. That's what the reduction ad absurdum allows me to do. And now my derivation is complete. I got to P. I early on assumed not P, with implication introduction. I've assumed not P. Now I write not P implies P, so I can cancel my assumption as well. And so now I have a derivation of not P implies P, and therefore I'm done.